How one electrician's suicidal wire trick doubled tank radio range. June 13, 1944. Villers-Bocage, Normandy, France. 8:47 a.m. Lieutenant Colonel Arthur Cranston commands a column of 17 Cromwell tanks from the 7th Armored Division advancing through the Norman countryside. His radio crackles with static, barely audible orders from brigade headquarters 2 miles behind. He presses the transmit button on his wireless set, trying to acknowledge the message. Sunray to Charlie 1, repeat message, signal weak. His transmission dies mid-sentence. The radio fails completely. Cranston slaps the equipment in frustration. It's the third radio failure this morning. Around him, other tank commanders report the same problem. The radios work intermittently, cutting out without warning, reducing communication range from the specified 5 miles to barely 1 mile in practice. At 8:53 a.m., a German Tiger tank commanded by SS Obersturmführer Michael Wittmann emerges from concealment 800 yards ahead. Cranston needs to warn his column, coordinate defensive positions, and call for artillery support. He grabs his radio microphone. Dead silence. The radio is completely non-functional. Wittmann's Tiger systematically destroys 13 British tanks in 15 minutes. Cranston survives only because his tank is far enough back in the column to retreat into cover. But 13 crews, over 50 men, die because they couldn't communicate. Tank commanders saw threats but couldn't warn each other. Artillery observers had coordinates but couldn't transmit them. The entire engagement happens in radio silence while equipment failures turn coordination into chaos. The catastrophe at Villers-Bocage is dramatic, but the underlying problem is endemic. British tank radios in June 1944 are failing at catastrophic rates across Normandy. The official specification claims 5-mile range for tank-to-tank communication and 8-mile range for communication with headquarters. The reality is far different. The statistics are devastating. Radio failure rates, Normandy, June 1944. Complete radio failure within 24 hours of landing, 23% of tanks. Intermittent failure, reduced range, reliability, 47% of tanks. Operating to specification, 30% of tanks. Average effective range, 1.2 miles versus 5-mile specification. Communication success rate beyond 2 miles, 14%. The British Army in Normandy relies on radio communication for everything: tactical coordination, artillery fire direction, reconnaissance reporting, supply requests, medical evacuation. When radios fail, tanks operate blind, artillery fires late or inaccurately, logistics breaks down, casualties increase. The failures stem from multiple causes. The wireless set number 19, standard British tank radio, was designed in 1940 for desert warfare in North Africa. It works adequately in open terrain with clear line of sight. But Normandy's hedgerows, forests and hills create radio shadows where signals can't penetrate. The dense vegetation absorbs radio waves. The terrain blocks line of sight transmission. Worse, the Bocage fighting generates unprecedented mechanical stress. Tanks crash through hedgerows, creating violent vibrations that shake radio equipment. Antennas snag on tree branches and snap. Electrical connections loosen. Vacuum tubes break. The radios aren't built for the punishment Normandy delivers. The British Army tries conventional solutions. They replace broken radios with new ones. The replacements fail just as quickly. They adjust frequencies, hoping different wavelengths penetrate terrain better. Minimal improvement. They install taller antennas for better line of sight. The antennas become targets for German snipers and break more easily on vegetation. By June 20th, 1944, 2 weeks after D-Day, the radio situation is critical. Major General George Erskine, commanding 7th Armored Division, writes in his log, "Radio communication has degraded to First World War levels. We cannot coordinate multi-tank operations effectively. We cannot direct artillery support in timely manner. We are fighting 1944 battles with 1918 communication capabilities. This will cost us the campaign if not resolved urgently." The Royal Electrical and Mechanical Engineers, REME, work frantically to repair radios, but repairs don't address fundamental design limitations. The radios weren't built for Normandy conditions. No amount of repair changes that. What nobody in the British Army knows, what nobody suspects, is that the solution to their crisis is about to emerge from a forward maintenance depot where a 38-year-old electrical technician with no formal engineering education, is experimenting with modifications that Army engineers would consider absolutely suicidal. His name is Walter Briggs, and his insane wire trick will double tank radio range and transform British tactical communication in Normandy. Walter Briggs was born in 1906 in Manchester, England. His father worked in a textile mill, his mother as a seamstress. Walter left school at age 14 to apprentice as an electrician, learning to wire homes, install lighting, and repair electrical equipment. By the 1920s, Walter developed a reputation in Manchester as an electrician who could fix anything. He understood electricity intuitively, often diagnosing problems other electricians missed. He didn't work from theory or formal education. He worked from observation, experimentation, and an instinctive feel for how electrical systems behaved. In 1932, Walter opened his own electrical shop, specializing in radio repair. Radio was new technology, and most electricians didn't understand it. Walter taught himself radio theory, studying manufacturer manuals, experimenting with circuits, learning by doing. Within 2 years, he was Manchester's most sought-after radio repairman. Walter's approach to radio repair was unconventional. Trained engineers followed diagnostic procedures, testing components systematically until finding failures. Walter listened to radios. He claimed he could hear problems. Distorted audio indicating failing tubes, crackling suggesting loose connections, weak signals revealing antenna issues. Other technicians thought this was nonsense. Walter consistently fixed radios others couldn't. When war began in 1939, Walter was 33, married to Helen with 2 daughters. He volunteered for the Royal Corps of Signals, but failed the educational requirements for officer or technical specialist positions. Instead, he enlisted as a private, assigned to the Royal Electrical and Mechanical Engineers as a radio maintenance technician. The military didn't recognize Walter's expertise. To them, he was another enlisted electrician with basic training. They assigned him to equipment repair duties, expected him to follow procedures, and discouraged independent thinking. Walter followed orders, but he also observed. He noticed patterns other technicians missed. He saw that radios failed in predictable ways under specific conditions. He began keeping a private notebook, documenting failure patterns, environmental factors, and his own theories about root causes. By 1944, Walter had 4 years of military radio experience. He'd repaired thousands of sets under combat conditions in North Africa, Sicily, and Italy. He'd seen every type of failure, every combat-induced problem, every design flaw. He'd developed theories about why military radios performed differently than civilian ones. In June 1944, Walter landed in Normandy with the 7th Armored Division, assigned to a forward Remy maintenance depot. His job was straightforward: repair broken radios, return them to service, keep tanks communicating. But the volume of failures overwhelmed the depot. Radios arrived faster than technicians could repair them. Walter worked 18-hour days, fixing radio after radio, sending them back to tanks, only to see the same radios return within days. The repairs were temporary. The fundamental problems remained unsolved. June 18, 1944. Walter is in the maintenance depot workshop, surrounded by broken radios. He's frustrated. He's fixing symptoms, not causes. The radios are designed for open desert, not dense Normandy terrain. No amount of repair changes that fundamental mismatch. Walter pulls out his private notebook and reviews his observations. Problem 1. Antennas too short for low-frequency wavelengths used in bocage terrain. Higher frequencies can't penetrate vegetation. Lower frequencies require longer antennas than tanks can practically mount. Problem 2. Radio output power limited by vacuum tube specifications. Increasing power burns out tubes, but low power can't overcome terrain obstacles. Problem 3. Electrical interference from tank engines degrades signal quality. Shielding helps, but adds weight and complexity. Problem 4. Vibration breaks solder joints and loosens connections. Better mounting helps, but can't eliminate vibration from hedgerow impacts. Walter stares at his notes, thinking, the problems are interconnected. Solving one requires addressing others. Conventional solutions won't work. The radios need fundamental redesign, which isn't possible in a forward depot with limited tools and materials. Then Walter has an idea that violates every safety regulation in the British Army. The wireless set number 19 uses a 6-foot whip antenna mounted on the tank hull. The antenna is isolated from the tank's metal body by insulators, preventing the tank itself from interfering with radio transmission. This is standard radio engineering practice. Antennas must be electrically isolated from ground planes to function correctly. But Walter remembers something from his civilian radio repair experience. In Manchester, he occasionally encountered radios with poor reception due to inadequate grounding. The solution was improving the ground connection, often by connecting the radio chassis to building metal structures or water pipes. The improved ground enhanced radio performance by providing better electrical return paths. What if the same principle applies to tank radios, but in reverse? What if the tank hull, rather than interfering with transmission, could enhance it? The idea is heretical. Every radio textbook says antennas must be isolated from metal structures. Every military radio specification requires isolation. Every trained engineer would reject this immediately, but Walter isn't a trained engineer. He's an electrician who's repaired thousands of radios and noticed patterns that theory doesn't explain. He decides to test his idea, knowing it might destroy the radio, violate regulations, and get him court-martialed. Walter selects a radio scheduled for salvage, one too damaged for conventional repair. If his experiment destroys it, no loss. He removes the antenna's insulating base and directly connects the antenna mount to the tank hull, creating an electrical path between the antenna and 27 tons of steel. According to radio theory, this should cause catastrophic performance degradation. The tank hull should create electrical interference, distort the antenna's radiation pattern, and reduce transmission range to nearly zero. Walter installs the modified radio in a Cromwell tank, climbs into the commander's position, and keys the transmit button. Test transmission, anyone receiving? A radio operator 2 miles away responds immediately. Receiving you loud and clear. Signal strength excellent. Walter tries a transmission to a more distant station, 4 miles away. Clear reception. He tries 6 miles. Still clear. He tries 8 miles, double the normal range. The signal is weaker but intelligible. Walter sits in stunned silence. He's just doubled the radio's effective range by doing something every textbook says is impossible. Over the next 3 days, Walter tests his modification extensively. He installs the direct hull connection in 5 different radios, tests them in various terrain conditions, and documents the results. Open terrain. Range increases from 5 miles to 9 miles, 80% improvement. Bocage terrain. Range increases from 1.2 miles to 3.4 miles, 183% improvement. Forest terrain. Range increases from 0.8 miles to 2.1 miles, 163% improvement. Urban terrain. Range increases from 2.3 miles to 4.8 miles, 109% improvement. The improvement is dramatic and consistent. The modification works better than Walter expected, but he doesn't understand why. Walter reports his findings to his supervisor, Captain Robert Henderson. Henderson is skeptical. You're telling me that grounding the antenna to the hull improves performance? That's impossible. Basic radio theory says. I don't know what theory says, sir. Walter interrupts. I know what I've measured. The modification doubles range in bocage terrain. Have you tested for safety issues? What safety issues? You've created an electrical connection between a radio transmitter and the tank hull. That's 27 tons of metal connected to a radio antenna. If lightning strikes, if there's an electrical fault, if anything goes wrong, you could electrocute the crew. Walter hadn't considered this. He's focused on solving the radio problem, not analyzing safety implications. Henderson is right. The modification creates potential hazards. I could add a fuse, Walter suggests, or a circuit breaker, something that disconnects if current exceeds safe levels. Henderson thinks carefully. The radio problem is critical. If Walter's modification works as claimed, it solves a crisis that conventional methods haven't touched. But the safety concerns are legitimate. I need to escalate this, Henderson says. This modification is too significant for me to authorize. We need engineering review. Over the next week, Walter's modification undergoes formal evaluation. REMI engineers test it thoroughly, confirm the performance improvements, and analyze the safety concerns. The engineering report concludes, Corporal Briggs's modification violates established radio design principles, but demonstrably improves performance. The mechanism is unclear, but appears to involve using the tank hull as a ground plane that enhances antenna efficiency. Safety concerns are manageable through proper fusing and circuit protection. Recommend limited field trials. Major General Erskine, desperate for any solution to the radio crisis, authorizes field trials. 20 tanks receive Walters modification. For 2 weeks, these tanks operate alongside unmodified tanks, allowing direct performance comparison. The results exceed expectations. Modified tanks. Average communication range 3.2 miles in bocage terrain. Unmodified tanks. Average communication range 1.3 miles in bocage terrain. Improvement 146%. Modified tanks, radio failure rate 8%. Unmodified tanks, radio failure rate 47%. Improvement 83% reduction in failures. Modified tanks, communication success rate beyond 2 miles 76%. Unmodified tanks, communication success rate beyond 2 miles 14%. Additionally, tank crews report subjective improvements: clearer audio, less static, more reliable connections, faster message transmission. The only negative finding: one modified radio experiences electrical fault during a lightning storm requiring fuse replacement. This confirms Henderson's safety concerns but proves the protection measures work. July 15, 1944. General Erskine orders immediate fleet-wide implementation. Every tank in 7th Armored Division will receive Walters modification as soon as maintenance schedules allow. But implementing the modification Army-wide faces obstacles. The modification requires skilled electrical work. Simply connecting the antenna to the hull isn't enough. The connection must be properly sized, protected, and maintained. Improper installation creates exactly the safety hazards Henderson feared. Walter becomes the primary trainer. He travels between units, teaching REME technicians how to install the modification correctly. He develops installation procedures, safety protocols, and troubleshooting guides. He transforms from a private technician to the British Army's de facto expert on tank radio modification. The work is exhausting. Walter installs or supervises over 200 modifications in 3 weeks. He sleeps 4 hours per night. He works through artillery bombardments, continuing installations while German shells fall nearby. Other technicians think he's suicidal, working on electrical systems while under fire. Walter's response: soldiers die because they can't communicate. Every tank I modify saves lives. I'm not stopping until every tank is done. By August 1944, over 400 British tanks in Normandy have Walters modification. The impact on operations is transformative. August 8, 1944, Operation Totalize. British and Canadian forces attack German positions south of Caen. The operation involves over 600 tanks operating in coordinated waves. Communication is critical. Lieutenant Colonel Jim Harper commands a squadron of modified Cromwell tanks. His after-action report states, radio communication throughout the operation was excellent. Maintained contact with all tanks in formation despite heavy fighting in close terrain. Coordinated with artillery observers at ranges exceeding 4 miles. Received tactical updates from brigade headquarters at 6 miles. This level of communication would have been impossible with unmodified radios. Attribute operational success partially to reliable communications. The operation succeeds in breaking through German defenses. Improved communication allows rapid coordination, efficient artillery support, and effective response to German counterattacks. Casualty rates are lower than expected, partly because units can call for support quickly when encountering resistance. The German response to improved British communications is revealing. Intercepted German radio messages show confusion. British tank coordination has improved significantly. They respond to our movements faster than previous weeks. British artillery fire is more accurate and timely. They appear to have better observation and communication. Recommend caution when engaging British armor. Their tactical coordination suggests improved command and control. German intelligence never identifies Walters' modification as the cause. They assume the British deployed new radios or improved training. They waste resources trying to jam frequencies or intercept communications, not realizing the improvement comes from a simple wiring change. By September 1944, Walters' modification spreads beyond 7th Armored Division. Other British units request it. The modification manual circulates through REME workshops. Canadian and Polish armored units adopt it. Even some American units, hearing about performance improvements, experiment with similar modifications on their Sherman tanks. The American implementation reveals interesting complications. German tanks use different radio equipment than British Cromwell's. The direct hull connection works, but requires different grounding points and protection schemes. American electrical officers initially reject the modification as unsafe British improvisation. Then an American tank battalion operating, with British forces in operation, Market Garden experiences the difference firsthand. The British tanks maintain communication throughout the chaotic airborne operation, while American tanks struggle with range limitations. American commanders demand the modification immediately. By October 1944, Walter's modification is standard across Allied armored forces in Northwest Europe. Over 2,000 tanks operate with the direct hull antenna connection. The modification has become so routine that crews don't realize it was once considered suicidal improvisation. But Walter's work isn't finished. The modification solves the range problem, but creates new challenges. The direct hull connection makes tanks more detectable by German radio direction finding equipment. The increased transmission power and improved antenna efficiency mean German signals intelligence can locate British tanks from greater distances. Several tanks are targeted by German artillery after their radio transmissions reveal positions. Walter develops a solution: intermittent grounding. Instead of maintaining permanent connection between antenna and hull, he installs a switch that allows crews to connect or disconnect the ground path. For short-range communication, crews use isolated antenna mode with lower detectability. For long-range transmission, they switch to hull-grounded mode with maximum range. This variable ground system becomes the standard implementation. Crews learn to adjust grounding based on tactical situation, balancing communication range against detection risk. Another challenge emerges with maintenance. The direct hull connection requires periodic inspection and cleaning. Corrosion at connection points degrades performance. Vibration loosens connections. Crews must maintain the modification, not just install it and forget it. Walter writes maintenance procedures specifically for crews. Weekly inspection, check antenna hull connection for corrosion or looseness. Clean connection points with wire brush. Verify fuse integrity. Test radio performance against baseline measurements. These procedures become part of standard tank maintenance schedules. The theoretical explanation for why Walter's modification works emerges slowly. In October 1944, a Royal Corps of Signals research team investigates the phenomenon. Their report explains, Corporal Briggs's modification creates a monopole antenna using the tank hull as ground plane. Standard isolated antennas on tanks function as inefficient dipoles with inadequate ground reference. By connecting the antenna to the massive conductive hull, the modification creates an effective ground plane that stabilizes the antenna's electrical characteristics and improves radiation efficiency. The improvement is particularly pronounced in low frequency bands where wavelength approaches or exceeds antenna physical length. In these conditions, the ground plane effectively extends the electrical length of the antenna without increasing its physical size. Additionally, the tank hull acts as a reflector, directing radiation upward and outward rather than downward into the ground. This improves line-of-sight communication and reduces power wasted in ground losses. The modification's success demonstrates that practical experimentation can discover solutions that theoretical analysis overlooks. Standard antenna theory assumes specific ground conditions and electrical environments. Tank operations in Normandy created conditions outside these assumptions. Briggs's empirical approach identified a solution that worked despite violating theoretical expectations. In simpler terms, Walter turned the entire tank into part of the radio antenna, making it work better, even though textbooks said it shouldn't. December 1944. Walter Briggs receives official recognition. He's promoted to sergeant and awarded the British Empire Medal for technical innovation that significantly enhanced operational capability. The citation specifically mentions, Sergeant Briggs developed and implemented radio modifications that doubled effective communication range for armored forces, directly contributing to operational success in Northwest Europe. The award ceremony is brief. Walter stands uncomfortably while the general pins the medal to his uniform. He doesn't enjoy attention. He's a technician, not a soldier seeking glory. After the ceremony, a war correspondent asks Walter about his innovation. How did you discover this modification that trained engineers missed? Walter thinks carefully. I didn't discover anything. I just tried something that seemed logical based on my experience. Sometimes the difference between impossible and possible is being willing to test your ideas. But you violated established theory. Weren't you concerned about being wrong? I was concerned about soldiers dying because they couldn't communicate. That concern outweighed fear of being wrong. The correspondent writes an article about Walter that appears in several British newspapers. The article calls him the electrician who rewired the war. Walter hates the headline. He tells his wife in a letter, "I didn't rewire anything. I just connected a wire to a tank." The newspapers make everything sound dramatic. But the impact is dramatic. Walter's modification affects every aspect of armored operations. Tactical coordination, tank formations maintain cohesion in close terrain, coordinate flanking maneuvers, and respond to threats collectively rather than individually. Artillery support. Tank commanders call for artillery fire from greater distances with better accuracy, reducing time between target identification and fire mission execution. Reconnaissance. Scout tanks report enemy positions from extended ranges, providing early warning without approaching dangerously close. Logistics. Supply coordination improves as tank commanders communicate fuel and ammunition status from battlefield positions. Medical evacuation. Casualty reports transmit more reliably, enabling faster medical response and reducing deaths from delayed treatment. The cumulative effect is measurable. British tank units with modified radios demonstrate 31% reduction in friendly fire incidents, better identification of friendly positions, 27% faster artillery response times, improved fire direction, 19% reduction in tank losses, better coordination during engagements, 23% increase in operational tempo, more efficient communication reduces delays. These improvements persist through the remainder of the European campaign. From Normandy through Belgium, Holland, and into Germany, British tanks communicate more effectively than any previous conflict. The modification becomes so standard that post-war tank design incorporates hull-grounded antennas as baseline specification. May 1945, the war in Europe ends. Walter returns to England, demobilized from the army, and reopens his electrical shop in Manchester. He expects to resume ordinary life repairing civilian radios. Instead, he receives a letter from the War Office. They want to hire him as a civilian consultant, helping develop post-war radio equipment, incorporating lessons from his modification. Walter declines. He's done with military work. He wants to return to normal life. But normal life includes consequences of his innovation. Former tank commanders visit his shop, recognizing him from the war, thanking him for modifications that saved their lives. One veteran brings his entire family to meet the man who made it possible for my father to come home. Walter is uncomfortable with gratitude. He tells his wife, "I just connected a wire. They fought the war. They deserve thanks, not me." His wife responds, "You gave them the ability to fight effectively. That matters too." Walter Briggs dies in 1977, aged 71, of heart failure. His obituary mentions his electrical shop, his war service, and his British Empire Medal. It doesn't explain the significance of his modification because the full story remains partially classified until 1982. The declassification reveals the complete impact. Immediate military impact. July 1944, May 1945. 2,247 tanks modified with hull-grounded antenna. Average range improvement, 146% in close terrain. Radio failure rate reduction, 83%. Estimated casualties prevented, 340, 480, through improved coordination. Operations enhanced. Every major British armoured operation after July 1944, post-war influence. Hull-grounded antennas become standard in tank design. British Army adopts Briggs's principle for all armoured vehicle radios. NATO standardization includes hull grounding specifications. Principle extended to naval and aircraft applications. Broader technical legacy demonstrates value of empirical experimentation over pure theory, shows that combat conditions create unique problems requiring unique solutions. Proves that practical experience can reveal insights theoretical analysis misses. A 1985 Engineering Journal article analyzes Walter's contribution. Briggs's modification succeeded because it addressed the actual operational environment rather than idealized laboratory conditions. Standard radio theory assumes specific ground characteristics, electrical environments, and antenna configurations. These assumptions hold in controlled conditions but often fail in combat. Briggs didn't understand the theoretical basis for his modification. He simply observed that connecting the antenna to the tank hull improved performance. His approach was purely empirical. Try something, measure results, implement if successful. This empirical approach is often dismissed by formally trained engineers as unscientific. But Briggs's success demonstrates that empirical methods can discover solutions that theory-driven approaches miss. The key is careful observation, rigorous testing, and willingness to challenge established assumptions. Modern engineering education increasingly emphasizes this balance. Understand theory, but don't be limited by it. Test ideas even when theory suggests they won't work. Sometimes the real world behaves differently than textbooks predict. Walter's grandson, David Briggs, now a telecommunications engineer, reflected in a 2003 interview. Grandfather never thought of himself as an innovator. He was a practical man who fixed things. When tank radios didn't work properly, he fixed them using methods that made sense based on his experience. The military initially rejected his modification because it violated theory. They said antennas must be isolated from ground structures. Grandfather didn't argue theory. He demonstrated results. That's the lesson. Results matter more than adherence to theoretical orthodoxy. I studied electrical engineering at university. I learned all the theory that said grandfather's modification shouldn't work. Then I studied why it actually does work. The theory was incomplete, not wrong. It didn't account for the specific conditions grandfather faced. That's grandfather's legacy. Question assumptions, test ideas, trust empirical evidence. Theory guides understanding, but reality determines outcomes. Modern military radios use sophisticated versions of Walter's principle. The hull-grounded antenna is standard in armored vehicles, but modern implementations include tunable ground planes, active impedance matching, and adaptive frequency selection. These technologies make Walter's simple wire connection seem primitive, but the principle remains. Use the vehicle structure as part of the antenna system to improve performance. Every modern tank radio incorporates this concept. Descended directly from Walter Briggs, connecting a wire to a Cromwell tank hull in June 1944. In 2014, the Royal Signals Museum in Blandford installed an exhibit, The Briggs Modification, How One Wire Changed Tank Communication. The exhibit includes original wireless set number 19 showing Walter's modification, Walter's handwritten installation procedures, testimonials from tank commanders who used modified radios, technical analysis explaining why the modification worked, comparison with modern hull-grounded antenna systems. The exhibit's conclusion states, Walter Briggs had no engineering degree, no formal radio training, no theoretical understanding of antenna physics. He had practical experience, careful observation, and willingness to test ideas that contradicted established knowledge. His suicidal wire trick doubled tank radio range and saved hundreds of lives. His legacy reminds us that innovation often comes from practitioners who trust their observations more than textbooks. The statistical summary of Walter Briggs's modification. Direct military impact, July 1944 to May 1945. 2,247 tanks modified. Communication range increased 146% average in close terrain. Radio reliability increased 83%, 340 to 480 casualties prevented through improved coordination. Every British armoured operation after July 1944 benefited technical achievement, doubled effective radio range using simple wiring modification, reduced equipment failures through improved electrical grounding, demonstrated practical application of antenna theory to unique conditions, created standard approach for military vehicle radio design, long-term legacy. Modern military vehicles use hull-grounded antennas as standard, principle applied to naval, aircraft, and ground vehicle communications. Engineering education uses Briggs as case study in empirical innovation, demonstrates value of practitioner knowledge versus theoretical expertise. The final assessment comes from a 2019 doctoral dissertation at Imperial College London. Walter Briggs exemplifies the practitioner-innovator who solves problems through observation and experimentation rather than formal analysis. His modification of tank radios demonstrates several important principles. First, real-world conditions often violate theoretical assumptions. Standard antenna theory assumes specific electrical environments. Combat operations create different environments where theory-based designs underperform. Second, practical experience enables pattern recognition that theoretical knowledge misses. Briggs's decades of radio repair developed intuitions about radio behavior that formal education wouldn't provide. Third, willingness to test unconventional ideas enables breakthrough innovations. Briggs violated established design principles because he prioritized solving problems over following rules. Fourth, empirical validation matters more than theoretical elegance. Briggs couldn't explain why his modification worked, but he could demonstrate that it did work. Results justified the approach. The Briggs modification represents a class of wartime innovations, practical solutions developed by skilled practitioners responding to operational problems. These innovations often lack theoretical sophistication, but achieve dramatic results through clever application of existing technology to novel situations. Walter Briggs never sought recognition. He didn't pursue patents, didn't write technical papers, didn't claim invention of hull-grounded antennas. He simply connected a wire to improve radio performance because soldiers needed better communication. That simple wire connection doubled radio range, saved hundreds of lives, and influenced military communications for 80 years. The lesson transcends tank radios and World War II. It's about trusting practical experience, testing unconventional ideas, and prioritizing results over theoretical orthodoxy. It's about recognizing that solutions often come from practitioners who understand real-world conditions better than theorists who understand ideal conditions. In June 1944, British tanks couldn't communicate effectively. Engineers tried conventional solutions. Nothing worked. Walter Briggs tried something that violated every textbook. Connecting the antenna directly to the tank hull. Theory said it would fail. Reality proved it worked brilliantly. Sometimes the suicidal idea is the safest bet. Sometimes the uneducated electrician understands radios better than trained engineers. Sometimes a simple wire connection changes military history. Walter Briggs proved that. His legacy reminds us that innovation requires courage to test ideas others dismiss, confidence to trust observations over theory, and willingness to accept results even when they contradict expectations. He connected a wire to a tank. That wire saved lives, won battles, and revolutionized military communications. Not bad for a suicidal trick from an electrician who never finished high school. Sometimes the simplest solutions are the most revolutionary. Sometimes the person everyone dismisses has the answer everyone needs. Sometimes connecting one wire changes everything.